Okay, so it's time to start the session and actually start the first talks from the conference. So this year we decided to start with a big splash, and the first session is about, the highlights of the conference. As you might know, it's always a big challenge to select the best papers, students' papers. At STOC usually we have a few dozen of fantastic submissions. It's always a big task to select them, but usually, the selected papers are among the best papers in a given year in the whole theory community. So it's really my pleasure to host this session and to start with the very first speaker, Michail Ostrovskii, in a joint with Chris Gartland, will be presenting the best paper talk, lower estimates for 𝐿1-distortion of transportation cost spaces, and just the final thought. So this is the presentation, and I hope all of you will be able to join us also for the awards session, where during the business meeting we'll be giving the certificates. So let Michail start the talk.
Okay. I would like to thank the organizers for this opportunity, and let me start promptly. So we are going to talk about finite metric spaces. We denote them XD, and without loss of generality, we may assume that X is a finite graph, and DUV is the shortest path distance. And the key example for us will be planar grid. Normally, it will be square grid, which we denote, like you see, it is how I denote square grid with Manhattan distance. So it is a normal shortest path distance, as I sketched on that diagram. And we shall talk about transportation cost and transportation problems. So transportation problem is a signed measure on XD. So what it means, that in some points of finite metric space, we have positive, they are blue on this diagram, and in some we have negative, and total is 0. And we consider this as a transportation problem. We need to move from positive to negative so that everywhere it will be 0. And of course, to do it, we need to design a transportation plan, which is a representation of this form. AI is the amount of product which we move from xi to yi. It is how it looks on the diagram, so that everywhere it will be 0. And the transportation cost of such measure is, for each plan, we form such sum, the amount of product times distance. This is the cost of a plan. Then we consider infimum over all plans. In finite case, of course, it is attained, and it is transportation cost of that measure mu. And we shall also recall definition of earth mover distance, which is just the cost in the described sense of the difference of two probability measures. And applications. Applications of earth mover distance, one is computer vision. It is standard. And there are some other emerging applications, for example, for word mover distance between two documents. And here I cite one paper on that matter. And computing earth mover distance. In general, it is not a hard problem. It can be done in polynomial time and actually rather fast. But the problem is that in applications, for example, for approximate nearest neighbor search, one must to compute many EM distances, and existing algorithms are too slow at this scale. And Indyk-Thaper in 2003, they suggested using embeddings of earth mover distance in 𝐿1 with low distortion. On next slide, I shall recall what is distortion. And they used, after that, they used fast approximate nearest neighbor search algorithm in 𝐿1-D. So, and as a consequence, this activated the study of embeddings of transportation cost space and EMDX into 𝐿1. Now reminders. 𝐿1-D space is just RD with this norm. and the corresponding distance. Distance between two vectors is the norm of the difference. And L1 distortion of a metric space Z is the following. We map that metric space into L1D, as you see here. And then we consider such constant D for which this is true. We consider embeddings for which this is holds, and find infimum D for which it can hold. And this is called L1 distortion. And in this talk, I shall use the following general fact, which is very useful fact, that for transportation cost on X and for earth mover distance on X, the L1 distortion is the same. And for transportation cost, we may restrict our attention to linear maps, which makes it easier. It is a very useful fact. Now, known estimates. It started with approximation by trees. It is Bartal in 1906 and 98, then Charikar, then Fakcharoenphol, Rao, and Talwar in 2003. And I shall call these authors FRT because I shall mention them repeatedly. A key method for L1 embeddability is to approximate the metric space itself by random dominating tree matrix. I shall not explain what it means because it is a rather long explanation. But hopefully this definition gives some intuition. And key principle here is the following, that if metric space X admits a tree approximation with distortion D is a real number, positive real number, then L1 distortion of the transportation cost space and thus of earth mover distance is less or equal D. And fundamental bound, which belongs to FRT, is that a tree approximation distortion of X of a finite metric space X satisfies that distortion is big O of logarithm of cardinality, the number of elements in X. And thus, for distortion of transportation cost space, and so earth mover space, we have the same estimate. It is big O of logarithm of cardinality. And sharpness. It was immediately clear at the time when this was proved that this bound is tight for constant degree expanders. But a constant degree expanders is not the most interesting object for transportation cost. So the main question, important question, was whether this bound can be improved for decent spaces. And so for what finite metric spaces can we improve this general bound? And of course, by tree approximation, you can do something. Improvement is possible when X admits a random dominating tree approximation with distortion which is small o, lowercase o of log X. But it turns out that this class is rather restricted. And there is a sufficient negative evidence for this approach, that for many important families, for example, for grids, diamond graphs, such improved tree approximations are impossible. And here I list names of people who contributed to that. And now, after tree distortion did not work, what about L1 distortion in general? And there is the first example of a large distortion for good space was obtained by Khot and Naor in 2006. They proved that for Hamming cubes, for these standard Hamming cubes, the distortion is as large as it can be by FRT result. It is a logarithm of the cardinality. Logarithm of cardinality, and so it is theta of n. So this is maximal order allowed by FRT upper bound. And for planar grids, a year later, Naor and Schechtman did similar results, but they did not reach the FRT bound. They proved only bound with a logarithm of the square root of cardinality. square root of the logarithm of cardinality. And also a similar result was proved for diamonds. And here I recall what is a diamond. First we consider a quadrangle, then we replace each edge by a quadrangle, and so on, and you see how they look like. And here, Bodier, Gartland, and Schlumprecht proved results similar to Naor Schechtman's, that again it is at least square root of logarithm of cardinality. And here I would like to mention why we pay attention to recursive families. If the diamond and other families of graphs constructed in a similar recursive way play a significant role in various scientific areas, including physics, analysis, and computer science. And the earliest publication in which we made diamond graph is physics paper of Berker and Ostlund. And for these classes of metric spaces and for grids, the following natural question was open for a long time. Do there exist embedding for which the FRT bound is improved? And here, now I start to talk about our main results. And first is that we developed a simpler approach for proving lower bounds on 𝐿1-distortion compared to Naor Schechtman and Bodier, Gartland, Schlumprecht. And the main results, we of course proved only for low estimates. For upper estimates, it is a result of FRT. So both for planar grids and for diamonds, we proved that this is a distortion, 𝐿1 distortion, is equivalent to logarithm of cardinality of the space. And also this method which we developed can be used for many other recursive families of graphs. And the only family out of those which is rather well known is Laakso-type constructions. And for those, it is not for all, of course, of them. We have a description for which one we have, again, a logarithm of cardinality. And also we contributed to Indyk's problem. And the problem is the following. We consider in RD, in EMD of RD, set of uniform measures supported on a point set. Indyk in 2002 asked, what is the 𝐿1 distortion of this space? And our contribution is we proved that it is from below estimated by at least a logarithm of S. And ingredients is our bound for planar graphs, for planar grids, results of Naor and Schechtman in the same direction, and result of Giladi Naor Schechtman strengthening the Bourgain's discretization theorem. How we get a stronger result with a simpler proof? Both Naor Schechtman and our paper use a version of Sobolev inequality. The main difference is that in our paper, we have our Sobolev inequality is in a sense customized, and also it contains a mixture of exponents 1 and 2, while the discretized classical version used by Naor and Schechtman contains only exponent 2. And so here is our new Sobolev-type inequality. And this is the main idea. After proving this inequality, you can get the results for a bunch of spaces. And here, what is it? It is G is any function from vertex set of the graph. And we consider a big set of transportation problems, which is sliced into levels. And for them, we proved this Sobolev-type inequality, where here we have a mixture of exponents 1 and 2. And this is standard Sobolev norm for discrete in the discrete case. And mixing exponents, we succeeded to get rid of square root in results of Naor Schechtman. And customization allowed us to get a proof which can be used for other metric spaces, diamond and Laakso graphs. And that's it. Thank you.
Thank you very much for this talk. Any questions? suggestions or okay, are there any direct implications or applications of these results?
I would consider this result as mostly negative. It is like proving that some problem is NP-complete. But on the other hand, it also leads to the direction. We still don't know for what classes of metric spaces 𝐿1-distortion can be better than results of FRT. Because our results show that for these classical canonical spaces which people looked at, they are kind of the same up to a constant.
Yes.
But there still can be some others for which they are different. And also, it can, inside, say, plain grid or somewhere, we can try to find some subsets for which they differ.
Okay.
It can also work.
Thank you.
I guess you can confuse the 𝐿1-distortion lower bound is for transportation distance, right? Okay.
Yes, for the set of all measures with transportation cause distance norm.
Okay. So but for planar metrics, we do know that I guess under just planar metric distances, we know square root log and upper bound into 𝐿1. So
yeah, we knew that it is square root of logarithm of cardinality. Now we dropped square root. So before it was known, here is the result of Naor and Schechtman. There is square root in the formula at the end. Now we drop square root.
this is, I guess, yeah.
Thank you very much. So let's thank the speaker again.